Great. So on Monday, we were talking about gravitational fields and electric fields. So we started with the warm-up, and we were looking at this field here around the Earth, which is a gravitational field. And so we're looking here and we're saying, we're trying to figure out what the arrows represent and what these circles represent. And the first question says, do the circles or arrows represent the gravitational force? Well, if this object here, this here, was like a rock or something, we know that gravity would simply pull it down towards the Earth, right? So we know that this arrow here represents the direction of the gravitational force. Now in this case, it doesn't actually represent the force because the force will change as we get closer and closer to the Earth, but it certainly shows the direction of the force, okay? So the arrows represent the direction of the force, right? And so one way we can look at this is we can say that the gravitational field shows the direction of force, right, on any mass. Okay, so gravitational fields describe the force and energy of masses. Okay, so we have the mass of the Earth, and it's pulling on this mass, and it pulls in this direction. Okay, the second question though says, do the circles or arrows represent the potential energy? And this is meant to refer back to stuff that we've talked about. And if you recall, potential energy goes up, right, as we lift something up, right? Potential energy increases as you lift. Right? And so if you think of it, that means each one of these circles represents a different potential energy. This would be a low potential energy close to the center. It would be higher as we move farther and farther away. So each one of these circles, because they're at a constant elevation, represents a different potential energy. And so the circles represent the potential energy of a system. So when we see this gravitational field, right, we have two kinds of markings. We have arrows that show the direction of the field, and we have these circles that show the potential energy of the field. And there are two things going on here. One is that the force, the direction follows the arrows, but the force gets stronger as the arrows get closer and closer together. Similarly, the force gets closer as the potential energy lines get closer and closer together. So these lines are close together, which means that the force down here is larger. In other words, it takes a smaller distance to change the potential energy when the force is large than when the force is small. So out here, where the lines are far apart and the force is small, down here, the lines are close together and the force is large. Okay? So there are a bunch of things we can read from this, and we're going to be talking about both of these today. Now, we're going to watch this video, and I'm going to call it up and play it right now, and we'll stop periodically and talk. So let's go back to the beginning and hit play.
Today I want to take a look at electric fields. And to do that, I want to take a look back at something we're a little bit more familiar with, and that is gravity and gravitational fields. So if we take a look at something like the Earth, the force by gravity pulls any mass that we place near the Earth towards the Earth, according to Newton's law of universal gravitation. And while you've probably seen and used this equation quite a bit, the idea of a gravitational field isn't something that comes up all too often. And that's because in physics, we typically refer to the gravitational field around the Earth as something else, the acceleration due to gravity. See, this equation can be rearranged. And it's this term right here, which we refer to more commonly as the acceleration due to gravity.
Okay, I'm going to pause here because I want to take a look at that equation that that guy wrote. And so let's go back over here and let's take a look at the next thing. So the first thing I want to get to is that he said that most people refer to this as the acceleration of gravity, and that's true. But what we're trying to see here is that we can say that the force is equal to the field, right, times the mass, or times the thing that the field acts on, right? Maybe that makes sense, right? But what I'd like to say is that in the case of for gravity, for a gravitational field, right, then the force is equal to the field strength times the mass, because gravity acts on masses. So instead of worrying about this big complicated thing, let's simply say that this is the field, right? Right, so the gravity, right, the field strength, okay? And so this field thing can be described, we can think of this field as being the gravitational field is simply equal to the force per unit mass, okay? And so it's simpler this way, instead of worrying about gm1 m2 over r squared. By the way, when we covered it, we didn't call it r squared, we called it d squared for distance. They're using r for radius. But either way, we didn't use this, we don't care about this equation. I just want you to simply say that it's talking about the force per unit mass, right? And so we see these field lines, and they're close together here near the Earth where the force is stronger, and they're far apart away from the Earth where the force is weaker, right? And so we're going to describe this field, okay? But don't panic about all the mathy thing. We're not doing calculations here. This is a conceptual concept thing that we're doing here. And so I want you to just get the idea that we're describing, like if I put a 1 kilogram mass here, it would accelerate towards the Earth with a specific force. If I put a 2 kilogram mass here, it would accelerate towards the Earth with twice the force, right? And so, you know, bigger masses would have bigger forces, but they would both all be proportional to the gravitational field at that point. So this field is describing the force that would act on any mass placed in it. Let's go back to that YouTube video and see what he has to say.
Which here on the surface of the Earth is 9.8 meters per second squared. And we can show the magnitude and direction of the acceleration due to gravity using arrows. And these arrows show that regardless of where you are on the surface of the Earth, the acceleration due to gravity is always inward toward the center of the Earth. Now, given this function, the farther away a mass is placed from the Earth, the weaker the force by gravity is going to be. And we can show that reduction in acceleration due to gravity around the Earth by showing the arrows that are farther away from the Earth as being shorter. So what we've done here is we've created a sort of map which shows the acceleration due to gravity in both its magnitude and direction.
Okay, again, I'm going to pause, but let's take a look at this. And he's talking about how we can use these small arrows and big arrows. We never do this, okay? We're just going to draw continuous arrows here from, right? And so the arrows simply go inward. So we have an arrow going inward that right represents our gravitational field, right? And the way we represent the strength, or the way we read the strength off of this, is that when the lines are far apart, then the force is weaker. Right? And in here, where the lines are close together, right? That means that the force is strong. Okay, and so that's how we're going to read it off the chart. But I also want to go back to that circle idea that we were talking about before, that I was talking about before. And so let's draw a circle here, and you can see that we would have our potential energy close to the Earth, right, would be a constant as long as they stay at a constant elevation, right? So I can draw this potential energy line, right? And I would draw it look pretty circular if I could draw a neat circle around the Earth. Similarly, I could draw another one that was farther from the Earth. Oops, sorry, right? And then again, I could have some change in potential energy, right? So I would have a different potential energy at this height than I had at my first height. So again, I'd have a second circle going around the Earth, right? And then I could have a new potential energy line representing like another change in potential energy going way up here. And if I did that, you can see that as the potential energy lines are farther apart, that the force is getting weaker, okay? Because it takes a larger distance for the potential energy to change with a smaller force than it does with a bigger force. So again, the same is true here. When the lines are farther apart, that means that the force is going to be weaker. Okay, because it takes a bigger distance to change the energy. And so again, when they're closer together, then the force will be larger, right? So we're not going to sit there and worry about the math of it, and we're not going to sit there and draw different sized arrows. It's going to look like this, where we'll have energy lines and we'll have force lines, field lines, right? All right, good. So let's go back to the video and see what else we got.
In space around the Earth. And we call this map the gravitational field. And in a similar manner, we can map out the electric field around charges, showing not the gravitational force around them, but the electric force around them. Now you'll remember, the electric field is given by Coulomb's law, where K is Coulomb's constant, Q is the charge of each particle in question, and R is the distance between the particles. And much like with gravity, we can rearrange this equation.
Oops. Let's go back here.
Charge. So we show the arrows as acting inward.
I have no idea how to get rid of this. Okay.
Now, one thing I want to point out is that as these electric field lines get closer together, that's effectively saying the electric field is stronger. And so oftentimes what you'll see, and much like with gravity, we can rearrange this equation.
Well, that was unpleasant.
And this term in parentheses is what we call the strength of the electric field. And that electric field strength is measured in newtons per coulomb.
There we go.
And while the electric field may be a little bit hard to wrap your head around, I want you to realize this term for the electric field is simply relating the magnitude of the electric force, which is going to act on a charge, to the amount of charge which that charge possesses. Much in the same way, the acceleration due to gravity relates the force by gravity to the mass of an object which has been placed in a gravitational field. And just like with a gravitational field, we can map out the electric force around a charge. Now, unlike the gravitational force, which can only pull two masses together, the electric force can cause two charges to be attracted to one another or repel one another. And so because of this, we have to be a little bit careful in how we draw our electric field. So there's a convention which we adopt, and that convention is a little bit arbitrary. But the convention is we always show the electric field as showing the direction in which a positive charge will be pushed or pulled. So if we were to place a positive charge anywhere close to this larger positive charge, it would in turn be pushed away from this large central charge because, according to Coulomb's law, like charges repel. So we show the electric field as acting away from this positive charge, and we're also able to show that as a test charge is placed farther and farther away from this central charge, the electric field is going to be weaker and weaker. And the convention holds true when we show the electric field around this negative charge as well. If we were to place a positive test charge anywhere around this central charge, it would be drawn inward toward this central negative charge. So we show the arrows as acting inward. Now, one thing I want to point out is that as these electric field lines get closer together, that's effectively saying the electric field is stronger. And so oftentimes what you'll see is people draw electric field lines not as segments as though I've done here, but as continuous lines. And the magnitude or strength of the electric field is simply given by how close those lines are drawn.
Yeah. In fact, that's how they always do it. So let's go back to what he was saying before. First of all, he gives this whole big thing. And again, what I want you to focus on is not the math here. And so what we're trying to say is that the force, right, is equal to the field strength, in this case, times the charge, okay? And so the field strength tells us a lot about the force. So the direction of it tells us what direction the force will move in a charge, and the if we know the charge that we've put in the field, we can even calculate the force. Okay, so it's pretty much just this. So when we're looking at these field lines, it's telling us about the force acting on an object. Okay, so again, an electric field describes the force that acts on a positive charge, right? And so that's what we need to think about. It's like a map of how the force would act on a positive charge. Now, we're going to look at this and we're going to say, oh, okay, well, he's got these lines, but they're not going to actually draw lines in the way that the guy describes. Instead, what they'll do is they'll just draw straight lines across, and we'll put an arrow on them. So we'll say it goes across, right? Similarly, we would just simply connect a continuous line here. But you can see that as it gets farther from the positive charge, it's going to start getting pulled towards the negative charge. And so it'll go outward, but as it goes outward, it's going to start curving, because the blue charge will have a bigger and bigger effect on it, or the negative charge will have a bigger and bigger effect on it. And so what we'll have is this continuous field line going across, and it goes this way, right? Similarly on the top, because it should be symmetric, right? We should get a positive field line that goes away from the positive charge and towards the negative charge. And so we have this sort of loopy line going from positive to negative. And we can have a steeper line going out here, but it would still bend around as it gets farther from the positive charge. The negative charge would take over, and we would get a line looking like this. And we can do the same thing out here. Okay, so we would get these field lines that go from positive to negative. And so with electric field lines, one thing we can get is that field lines right? So they go away from positive charges and towards negative charges, right? We could also draw our lines of potential energy if we wanted to, and I want to. So let's draw these potential energy lines here, and I feel like that should work. And one thing we can see is that, around right close to the positive charge, it would look pretty much like gravity again. So I would have some line looking like this, right? Close to. Okay. But right here in the middle, it would just be a straight line. In fact, these potential energy lines are always perpendicular to the field lines. And so this is where the potential energy would be between the two. And again, we could have a second one, and it would look something more like this. It would go farther away out here. Whoa, hey, that's kind of crazy. And going like this. And so we could have these potential energy lines as well. And you can see that as they're closer together near the charge, right, we have a bigger force, right? See how the field lines are all close together near the charge, but they're spread out here. And so we can see here the force must be weaker. Let's change. Right, the force would be weak out here, but it would be quite strong near the where the field lines are close together. Right here, or right. So where the field lines are close together, we have a strong force, and where they're far apart, we have a weak force. Okay, just like with gravitational fields. But if we were following this, a positive charge would follow the purple lines, right? So another thing we would get is that a positive charge would follow the field lines, right? The arrows, right? A negative charge would go backwards along field lines. Okay, there we go. Now, that's the end of the video, but after that, we were looking at a handout to try to connect electric fields and the Van der Graaf generator. So you have a question sheet, and you can link to it in the module. And it had some questions about electric field and this Van der Graaf generator. So this girl puts her hands on the Van der Graaf generator, and we know that the Van der Graaf is positively charged. Now she's actually touching it, right? And so we expect that the conduction occurs, right? And so the positive charge will cause electrons to conduct off of the girl and onto the Van der Graaf, leaving her head, right, positively charged, right? And so we can answer some questions about it, and you should try to do so, okay? And we've talked about why her hair spreads out. If the hair is repelled from itself, right, then we would assume that the hair has, all of the hairs are charged, and they have a similar charge, right? They have like charges, and so they repel each other. The question is whether it's positive or negative. I want you to ponder that and answer the question. Now the question is, what forces are acting on it? And instead of thinking the normal force here, really we're thinking here, let's just say the force her scalp acts on it. Let's think like a tension force or the pull of her scalp, right? But what forces do we have, right? And if you think about it, there should be some force lifting her hair in the air, right? And if her hair has mass, right, then the earth should be pulling her hair downward, right? And if her hair is lifting in the air, what's stopping it from actually just leaving her head, right? So there probably is some force between her scalp and the hair. So you need to think which of these forces describe the lifting force, right, the weight of the hair, and the pull of her scalp on the hair to keep it from lifting off her head. Okay. Lastly, what you're going to do is think, hey, if we cut her hair in half, which of those forces will change? And what I want you to realize is that you have these formulas for a reason. So if we look back at the formulas, if we cut her hair in half, two things are going to change. One, the mass of her hair will change, right? It will become half as heavy, right? And that would affect one of the equations. The other thing you should realize is the hair gets half as long, and that's certainly going to show up as the distance in the denominator of our force equations, okay? And so you should have an idea of how that would affect the gravitational force or the electrostatic force, acting on your hair. So just for each force you identify, simply tell how shortening the hair would change the force on her hair, okay? And then when you're done, you can email it to me if you haven't done, if you didn't hand it in when you were in class. Okay, so hopefully that makes some sense. And that was the end of the class that we did. So